Hey, Mr. Pham, quick question.
Yes, sir.
Um, on your first one, you explained the common emitter. I agree with that, but I'm just looking at the wording. You got V into and V out two. Then on the other side, you got V out one, but you got VE. Is that supposed to be V in one?
What do you mean VGN1?
Okay, down the bottom where the sine wave is at. Did,
Okay, now,
maybe you just changed it, didn't be consistent, but should that be VN1 instead of VE?
oh, that means in the display they show the VE of the Q1.
Oh,
Okay,
with E being the emitter then.
right.
But that's the same as VN
In,
VN1, right?
right, V in of Q1.
Oh, yeah, okay, all right. I was just make sure I didn't get confused on
Yeah,
that.
that's the textbook they're using that way. Okay,
Okay, thank you.
welcome. Now, if we looking into this differential amplifier, now they will be, before we already talking about, they apply input to Q1 at the base, okay? And Q2 will be rounded. That we already done. Now we do another one. That means input now apply to Q2 and the Q1 will be rounded. Okay, the first thing you can recognize, Q2 when you apply input into the base output collector. So they will be a CE amplifier. Okay? CE amplifier, input positive, output negative. Input negative, output positive. Okay? And you understand you get a sine wave. Q2 emitter, they go to Q1 emitter. Okay? So Q1 input applied to emitter, output from collector. They will be common base amplifier. Input, output will be in phase. Okay? That's just telling you whole story about this circuit. If you get any question, anything, just
So
let
does
me. Yeah.
So does that mean that the generator that's on Q2, when you do Q1, the generator gets switched over to the emitter?
Now automatically you get a sine wave at the Q1 emitter. That coming from Q2 emitter.
Okay. I thought you gotta change when you do the first one, you got the generator on the base, and then
No.
when you do the second one, the generator on the emitter. It don't go that way.
Now, that only telling you, okay, when you apply a sine wave to the Q2, then you also get a sine wave here at meter.
Okay.
And that will be go into the at meter up to what?
Okay.
Only one generator.
So okay, so the first one is common emitter. So you're saying when you do the common base, it does it's the generator stays in the same location.
Yeah, nothing to do with Q1 at meter. Automatically you get sine wave from at
Okay,
meter up Q2.
okay. All right.
Okay, now we'll see. Mode of signal operation. Single-ended output input. When a differential amplifier is operated in this mode, one input is drowned and the signal is applied only to the other. Okay, so single mode, that means instead this is a circuitry symbol for differential amplifier. You get one input, you get two input, exactly the same here. Okay, one input, two input. Okay, everything circuitry here will be inside this symbol. And now they're using only one input. They apply input to input 1 of amplifier and input 2 rounded. That's what they call a single mode. And the output you can get one output at output 1 and another one. They will be opposite. Okay. And the same thing, you can apply to input 1 or you can apply to input 2. Okay? Now, differential input. That means they apply both signal to 1 and to 2. However, they're telling you, okay, this input must be opposite. They cannot be the same. Okay, this going up, this will be going down. Input going down, this input have to be going up. And the output will be, okay, this the output, and output will be opposite. Okay, that will be two opposite polarity.
Output 180 degrees out of phase.
Yeah, our phase. Signal applied. They must be opposite. Okay? See, what next? Common mode input. Both input are the same phase. Same frequency and same amplitude are applied to the input. You can see that one here and that one here identical. Okay? See what happened? The output are superimposed and they are canceled. That means output will be nothing. The thing is the signal to input 1, input 2, identical. Same thing. Okay? Resulting in zero output voltage. This action is called a common mode rejection. Common mode rejection means that this unwanted signal, okay, that will be telling you if the signal identical applied to input 1, input 2, they consider to be the noise. The noise, that means the unwanted signal. So that's why they have to be canceled out. Will not appear on the output, the desired signal. common mode signal. That means the noise generally are the result of pick up radiated energy on the input line from ASIN line. Okay, so basically any signal identical at the input of the amplifier considered to be the noise. That means the signal you don't want it, and the op-amp will cancel that out. Okay. Common mode rejection ratio, CMRR. The measure of amplifier's ability to reject common mode signal is a parameter called a common mode rejection ratio. This is a formula to calculate the common mode rejection. Okay. AV, differential voltage gain. Okay. And ACM is a common mode gain. Okay. The higher the CMRR will be better. Okay. The CMRR is often expressed in a decibel dB in this formula. If you want to calculate the CMRR in decibel, the formula will be 20 times log of AV. That means the gain of differential amplifier divided to ACM. Okay, ACM, that means common mode gain. The example, a differential amplifier has a differential gain voltage AV equal 2000 and a common mode gain 0.2. They want to know a CMRR expressed in decibel. This is not hard to do. Okay. First thing you should calculate the CMRR equal AV D divide ACM. AVD means differential voltage gain. ACM, that means common gain. You take 2000 divide 0.2, you get a 1000. Okay. And now, if you want it in dB, you have to using this formula. 20 times log of 1000. That given you 80 dB. Okay, any question for that example? Okay, if it's not, can you do for me number B, example number B? A differential amplifier has a different voltage gain, AV. Okay, common mode gain, 0.25. They same thing, they want to know CMRR, common mode rejection ratio, and in decibel. I'll have to do it and telling me what you get. First thing you have to tell me what's the equal and CM in decibel. Okay, do it and let me know what you get.
First number is 34,000.
Okay, you get 34,000.
Another zero. That's
34 times.
you need another zero.
Oh, sorry.
Yeah. And then the second one is 90.63. 90.63. See if anybody else get the same thing.
That's what I want. Someone have to let me know, is it a correction for calculation or no?
I got the same thing.
You do the same thing?
Yeah.
Okay, good. Well, I think I make sure you have to do it, okay? Not try to just watch it. Cannot get through that way.
So, Mr. Pham, the first number, 34,000, is just the ratio, correct?
Yeah, ratio between,
And then the second number, the dB, is the dB number, the actual decibel.
yeah, decibel. Decibel.
Okay.
Okay, now see what happened here. Okay, first thing, if you're looking into the picture, you will know that noise here, right? How do we know that's supposed to be a noise? VCM. Common mode. Okay. They given you. Okay. AV D 2,500. Okay. And CMRR 30,000. V in 1. 500 microvolt IMF. At the same time, a 1 volt. That means this is a 1 volt here. Okay. 1 volt. Okay. This is 1 volt. 60 hertz. Common mode interference signal appear on both input here. So basically this just a noise. Okay. The thing is the noise, so that's why they affect you input 1 and also input 2. Okay. Number A, determine common mode gain ACM. Okay. And the calculation here telling you common common mode rejection ratio, AVD divide ACM. That will be given you ACM equal AVD divide CMRR. That means 2,500 divide 30,000. Okay, they already given to you here. Okay, so that's why you can get 0.083. That's for ACM. Okay. Then they say express CMRR in dB. Then you using the formula CMRR 20 log 30,000. They given you 89.5 dB. Okay. And number C, they want to know IMS output. Okay. V in different, V in 1 minus V in 2. You see that? V in here. V in 2 nothing, means 0. So 0, okay, V in 1, 500 microvolt minus 0.2. You get my 500 microvolt. V
Hey,
out.
Mr. Pham, so
Yeah.
there is no V in two, is that correct?
Exactly.
Okay,
Only one input V in.
okay. V in one.
Correct. V out equal AVD times V in different. You take 2500 times 500 microvolt. You can get 1.25 VRMS. That will be telling you one thing. Okay. Input, okay, equal, let's see, V in 500 microvolt. So that's a very small signal. Okay. And the noise, okay, 1 volt. No way you can see not 5 microvolt inside 1 volt. So that's why they really need how to reject the noise, okay? And the output coming out will be 125 volt IMF. So now you understand the purpose of the common mode rejection. They try to cancel the noise. Now, another example. You can see this example the same thing like the one we just did it. That means the noise here, okay, same the noise. However, now they apply both input V in 1 and V in 2. You can see what the difference between V in 1 and V in 2.
Hey, Mr. Pham, on this one, V in one and V in two, if you look at those sine waves, they look a little bit different.
They have to be different. Tell me what you think. What different?
They definitely out of phase.
Perfect. They merge out of phase. What happens if they're the same phase? Maybe the same amplitude, the frequency, they supposed to be the noise also. Okay? You can see the big one, VCM12 here. Okay? They identical. So consider the noise. Okay? V in 1 and V in 2. That's your input, your voice. They must be opposite. Okay, 180 degree off phase. That's the basic.
What does the output signal look like?
We'll see. I don't know. See, for the different zone amplified so they given AVD 2500 CMRR 30,000 V in 1 equal V in 2 equal 500. At the same time, okay, 1 volt, 60 hertz common mode interference signal appear on both input. You understand this? Just the noise, okay? They want to know the IMS output. See how they calculate it. First thing, V in different, okay? Differential. V in 1 minus V in 2. So 500 microvolt minus to minus 500. That's why they must be opposite. Okay, so you get a 1 millivolt IMS. Okay, V out will be equal AVD. That means differential gain times V in different. So 2500 times 1 millivolt IMS, they given to you. The answer will be 2.5 VIMS. Okay. And number B, determine the VIMS interference voltage on the output IMS output. Okay, ACM equal V out CM divide V in CM. Okay, V out CM equal ACM times V in CM 0.083 times 1 volt. Okay. How come you get 0.083?
Is that from the
That means-
previous, is that from the previous page, Mr. Pham?
Yeah, that means you have to get the ACM. Okay.
Hey, can you go to the other page real quick? Yeah, in the letter A,
Right here.
Yeah, letter A is 0.083.
Okay. 0.083. Okay, that means ACM. So ACM times V in CM. Okay. ACM 0.083. V in is 1 volt. Okay. Remember, this is 1 volt. This is 1 volt. Okay. So basically, output they still get the noise, but the 83 millivolt. Okay. So that will be completely end of the differential amplifier.
It take a lot of studying to get that, Mr. Pham.
Not too much. That's okay. Okay. And now let's see. We go to operational amplifier. Okay, this is operational amplifier. Okay. You get 3 terminals. Input positive, input negative. Okay. And output here. This is the IC. Okay, op amp. inverting input to minus side, non-inverting input at positive side. Okay, and the output to power supply from plus minus 8 volt to plus minus 38 volt. You're working on the left volt. Normally they can using 10 plus 10 and minus 10 volt or 15 to minus 15 volt. Okay. Ideal op amp open loop gain AOL will be infinity. That means the open loop gain equal infinity. Okay. Input impedance. You can see if you're looking into the op amp, you can see between the input positive and the output positive. Okay. You get the input resistance impedance. They want it to be infinity. Why they want it infinity? That means they not allow current to flow into the op amp. Okay. Output impedance. This is the output impedance here. Go to the output. They want it to be 0. Okay. So when you're looking into the symbol here, you need to recognize that will be a differential amplifier. But they're using only one output, not two. Okay. And they will be telling you VD. What that means, VD? Differential input VD equal V in positive minus V in negative, and they equal 0. So that will be tell you what? It will be telling you, okay, V in positive equal V in negative. Okay. All the time, the voltage between input positive and negative, they will be equal. The thing is that's what they call input differential. Okay. That's just a basic definition. Okay. Now, this is practical op amp. You see that op amp, you will be working on the left volt. This I see here. Pin 1, 2, 3, 4, 5, 7, 6, 7, 8. They using only 8 pins. Okay. Practical op amp. High voltage gain. Very high input impedance. Very low output impedance. Wide bandwidth. Okay. That's the basic definition for the practical op amp, the one you're really working on. Now see what they say here. Practical op amp. Output voltage Vout equal V in positive minus V in negative and multiply by A means the gain open loop. Okay. VD, difference between two inputs, the gain, AOL, open loop gain, of 741 op amp. That means the op amp you're working on the left, 741. They will be close to 200,000. That means open loop. That from a manufacturer. When they build IC 741 op amp, the gain close to 200,000. Very, very big. The output of op amp is never higher than. This is a very important for you. Output op amp is never higher than power supply. You see that? Otherwise, the gain is 200,000, then you don't want to working on the op amp. Voltage is too high. However, they let you know output of the op amp, no matter what you do, output cannot be higher than power supply voltage. If you get a gain at 200,000, if you apply a one input voltage, the output is 200,000 volt, never happen. In that case, we can say the op amp will be saturated. Saturation. That means output can go maximum into positive power supply or go to maximum negative power supply at it. When input applied is too high, that force the op amp into what we call a saturation. Okay? And op amp output will be equal load minus saturation voltage. Look like it will be less than power supply 1.4 volt. Okay? If you're using the power supply 15 volt, then when they saturated, they can be equal 15 minus 1.4 volt. Open loop gain, AOL. E defined at amplify output amplification without any external feedback signal connect to it. And for typical operational amplifier, is about 100 decibel gigahertz. Now you can see here. Okay, an op amp had open loop gain AOL 200,000 with a power supply 15 volt minus 15 volt. And also, instead you have to get the V saturation less than 1.4. However, in this example, they given to you V saturation same as power supply. Now, what they want to do is they want you to complete VD and complete V out. I given you the example number 1. Input positive 20 microvolt, input negative 40. Okay, so basically VD. Okay, V in positive minus V in negative. Okay, that means you get 20 minus 40. Minus 20 microvolt. Okay. And V out equal the gain equal 200,000 times minus 20 equal, let's see, okay, 200,000 times 20 equal you get minus 4. So to complete that one, VD you get minus 20. And V out you get minus 4. Okay? Now you do choose numbers 8 for me. They already given to you the formula here. Okay, go ahead and do calculation. Okay, you have to do it. If you don't know how to do what to do, let me know. Okay, who done number 2? VD.
Did you get 70 micro, Mr. Pham? You see, 1, 2, 3, 4, 5, 6. I would say VD is 70 micro, but somebody got to check it. And then
70.
times 2. And then V out is 14,
You say 14 volt.
right? Hey, Mr. Pham, I don't know if I'm getting too far or you want to discuss it. I got 14 volts on that, but if I got 16 volts, then that wouldn't work, would it?
Cannot be 60.
You can't. In other words, you can't go past 15.
Right. That V saturation 15 volt plus or minus.
Right.
Output
It's-
cannot be higher than that.
Yeah, okay. Yeah.
So
Okay. Let's try number 3.
I want to verify number 2. Who else get
Oh,
the
number
same?
2.
I also got the same answers.
Okay, perfect. So make sure I said you have to do it, okay? So that okay. That okay. See, Mr. Smith, up until now, he did very good.
All right, Mr. Pham. So number 3, hold on just a second. 50, then it's minus 3, 4, 5, 8, 6, negative. So, minus 20 for VD micro,
You
Is that
say
what you got, Mr.
minus
Pan?
20.
you got minus 20? Minus 20 micro. And then that's times 200,000. I got -4.
I think that's the same thing like number 1, right?
Yes, some of the number 1, yeah. Yeah. So you want to verify number 3?
Now the thing is, if I'm looking into that, I see both they get negative, right? 20
Yeah,
microvolt.
yeah,
So output will be the same anyway.
yeah.
Go ahead and do number 4.
Okay, number 4. 20 micro. So, VD, did you get 140 micro
Okay, let's see, 140 micro.
for VD? Okay, time 200,000. 28, but 28, it wouldn't be what you want because you said saturation is 15, right?
Right.
So the answer that should go in there should be 15, right?
Perfect.
Because the calculated number, when you take 140 microvolts and multiply it times the AOL, the open loop gain, which is 200,000, when you multiply 140 microvolts time it, you get 28. But 28 is much larger than 15, so you settle for 15, which is the max to keep it from saturating.
Exactly. That means the op-amp is saturated. You cannot multiply by the gain.
Mm-hmm. Mm-hmm. 100 minus 18 to the 6. Okay, for number 5, let me see. 1, 2, 3, 4, 5. For number 5, do you get 145 micro?
Number 5, you get minus 100 minus 45.
Right. And I'm asking you for VD, did you
Oh.
get 1, 2, 3, 4, 5? Did you get 145 micro?
Negative.
Oh, negative. Yeah, that's right. It is negative. And then you multiply that times 200,000 times.
Exactly, to get the gain.
Once again, the same type of thing. Well, that one up top, we got 28 and you put in 15, but this one here, you get a negative 29, which is bigger than negative, which is different from negative 15.
So they already saturated.
Okay, so so now if you could explain the difference between number 4 and number 5, because number 4, you got plus 15 V out, and number 5, you got minus 15 V out, and number 4, you had initially 28. So I guess that's why you put plus 15, and number 5, you got minus 15 or minus 29. So you put in negative 15.
I will. After we complete that.
Oh, you going to explain it at the
Yeah,
end?
yeah, we have to explain to them.
Okay. All right. So you want us to just go through and do number 6, 7, 8?
Yeah, exactly.
Okay. All right.
We try to complete that one.
Okay. All right. 1, 1, 0, negative, minus. So did you get 65 for
Perfect.
VD?
Perfect, 65.
65. And then that's times 2, 1, 2, 3, 4, 5. And then 13. 65, yeah, there, and 13 in the other box. $13, yeah. Okay. Now we're on number 7. Okay, negative 100. That's what I got. Times 2, 1, 2, 3, 4, 5. Minus 20, but you can't have minus 20, so then it's got to be minus 15.
Okay.
Number 7, minus 15. Because it calculated the minus 20 though.
Mhm.
Okay, then the last one is 130. Okay, 1, 2, 3, 4. Okay, minus 40. I got minus 40. You got just plain 40.
You get minus 40.
Yeah, what you got plain 40? Oh, yeah, it's minus 40.
Minus 40.
And then negative 8. Yeah, in the VD box is minus 40 micro. That's what I got.
And output will be
Minus 8. So, Mr. Pham, you really need to go over like number 4, 5, and 8. The ones that go over 15.
yeah, I will.
Okay.
After this example.
All right.
So, you get any question about calculation for this example? Again, I'm telling you, the output of the op-amp Vout, they cannot be higher than V saturation. In this case, they given you V saturation is plus or minus 15 volts. Okay, that means the output you cannot get higher than either plus or minus 15 volts. Okay, any question about this example? Okay, now let's see. We need to get the room so I can explain to you. Hello? Yeah. Rồi sao? Không, ok. Tôi đang rồi, tôi đang dạy học. Ok, tôi đang dạy học online. Ừ. Let's see. Okay, we can using that back here. Okay. Okay, this will be V out. And we know output maximum plus 15 volt. And another one minus 15 volt. This is a VD. On this side, maximum will be 15 volt plus V saturate. And this side will be minus V saturate. Okay. So VD, okay, let's see, equal 20 microvolt. Minus 20 microvolt. Okay. I pick up one example here. Minus 20 microvolt. That will be VD. Okay. So from minus 15 volt to plus 15 volt, you want to calculate the VD. V out, sorry. Equal VD time gain. Okay. ALL. However, if the VD higher than, this is the VD maximum. And VD minimum. Okay. Then either the output they can go to positive saturation or negative saturation. So that's why if you're looking in here, first thing you see, VD equal 140 microvolt. Okay. That is the maximum. So basically, you have to know what the maximum for VD. How can we get the maximum for VD? Okay.
Mr. Pham, which one you doing?
I try to explain how come you get 15 volt.
Are you doing number 4 or number 5?
Right now, we will be doing number 1 first.
Oh, okay.
If you get 20 microvolt, okay, let's see what V out. V D equal V in, okay? Minus V in positive minus V in negative, okay? So if we calculate it, we get V out minus 4 volt, okay? So 4 volt will be in here. Okay. However, that's what we're talking about. VD minus 20 microvolt. And now we calculate to number 5. Okay. For minus 45. Let's see. We're doing number 4, 20 minus 120. 20 minus 120, you get plus 140. Okay. Now you can get, okay, VD, sorry. If you get VD equal 140 microvolt, you do your calculation. It's over 15 volt. So they have to be saturated. And saturated, they will be given you V out. Plus 15 volt. Okay? And now, when you calculate the next one, and now you can follow it. Okay. You get a minus
Mr. Pham,
45.
you forgot to let them know that once they get the VD, they got to multiply it times the AOL.
Right.
And whatever answer they get from that is what will determine whether it's going to be plus or minus 15. Because that when they multiply times the AOL, it might be higher or lower than negative or positive 15.
Right. Okay, now in here you already see that V out AOL times VD. After you calculate the VD here, you multiply by 200,000, you get V out. If the V out higher than 15 volt saturation, okay, then they will be saturated. Okay, so that will be telling you after you calculate it, you get the V out higher than 15. So output op amp saturated and the output will be equal 15. And also the same calculation. If you get the V out more negative than minus 15, then op amp is saturated and the voltage will be in minus 15 volt. That will be explained to you, okay? Why in here?
Hey,
You
Make
get
that go down some more, Mr. Pham.
15 and minus 15. Yet what?
You showing half the screen. Slide it down some. Yeah, right there.
You see that? When you get a 15 volt and minus 15 volt, maybe you don't know why. Okay? I given you explain again. When you get the VD 140, you take 140 times 200,000, you get a V out. If that V out higher than 15 volt, that means op-amp saturated. And they saturate, they will be equal V saturation 15. Okay? Or when you multiply by the gain, you get higher than negative V saturation. So op-amp is negative saturated, they will be minus 15. That will be telling you one thing. Output of the op-amp cannot be higher than V saturation. Okay? Either they go positive saturation or they go to negative saturation. Okay, quickly.
Hey, Mr. Pham, can we see that thing that you showed real quick?
Which one?
The one where you just was drawing it. Yeah, right there, right there.
You know that is saturated. Right?
Okay,
So basically, if we're talking about VD, if VD and if V are higher than blood 15, so op-amp is saturated. Okay?
got it.
And op-amp is saturated, the thing is they higher than 15, so output have to be equal 15 volt. Okay? If you calculate the V out more than minus 15, that means op-amp saturated, and they have to be equal minus 15. Only the voltage V out, okay, bit less than 15 or higher than minus 15, you can calculate it. Okay, that means take V out equal VD times AOL. If any voltage V out you calculation higher than saturation, either they will be on this side or they will be on this side. Depend on V out higher than 15 or V out more less than minus 15. They be saturated. Okay, this one. Single-ended mode. That only telling you apply input to one input, another you route. At this differential mode, okay, that means you apply both input, one to negative, one to positive. Okay. However, we emphasize here, input one, input two must be opposite. Okay. 180 degrees of phase. On the other one, you apply single input to negative, or you can apply input to positive. Only one. That's okay. However, again, when you apply to both, then signal must be opposite 180 degrees of phase. Okay, input offset voltage. The ideal op-amp produce 0 volt out for 0 volt in. Okay. Normally, to input op-amp, you apply connect to the ground, 0. Output supposed to be 0, but they not. Okay. But they not. So that's what we're talking about. However, a small DC voltage without error appear at the output when no different shown input voltage is applied. Is primarily caused a line mismatch of the base emitter voltage of the differential amplifier input state op-amp as specified and op-amp data sheet the input offset voltage VOS is the differential DC voltage required between the input to force output to 0 volt. Okay, I can tell you one thing. Normally, if the both input op-amp you connect to the route, 0 volt, output supposed to be 0. However, they not 0. You measure, you get 10 millivolt. That's voltage you don't want it. You want it 0, but they not. That's what they call offset voltage. Okay, so now when you do the left volt, you can see, okay, you get two input here. Okay, if you connect to the route, output here supposed to be 0. However, if it's not 0, okay, then what you need to do, you get pin number 1 and pin number 5 connect to the variable resistor. So you can adjust this variable until output with 0. Okay, that's what they're telling you here. Adjust for 0 output. When you're working on left volt, you have to do. Adjust the offset voltage. Connect port. That means this port here to pin 1 and pin 5. Connect both input op-amp to the route. Connect that to the route. Output supposed to be route, but if it's not, then you adjust that here until they get 0 volt. That's the offset voltage out. Okay, open loop. This is the open loop gain. That means no connection. AOL. Open loop gain output equal VOUT divided VIN. This is the closed loop. Okay, that means now you get a resistor RF connect to the negative, and you get RI connect to the negative. That's what they call a closed loop. Okay. Now try to understand this one. This stands for gain. in dB. Okay, that's what they say here. Voltage gain in dB. Okay, and this will be frequency domain. That is the frequency. Okay, like you get 10 power of 0. Okay, equal power 10 power of 0 equal what? Equal 1. 10 power of 1 equal 10. 10 power of 2, 100,000 so far. That unit will be in hertz. Okay, and they said this what they call critical frequency. Now, if you look at this point, okay, on this point you're looking to the left, what the gain equal. Mr. Smith telling me what the gain equal at this point.
What's the gain at what point?
This point right here. Can you see it? The yellow one.
Mr. Pham, there's a bunch of yellow ones there. You need to use your red pointers so we can see what you're talking about.
Okay, let's see. Right? Better?
Yeah, so what's the gain right there?
Yeah.
Well,
At that
it's
point.
um that's the mid-range, so that's minus 3 dB, right?
No. By looking into the display.
I don't know, Mr. Pham, my brain is racked right now. You're just gonna have to tell us.
Right at this point.
Yeah, that's well, I'm just looking at it. It says mid-range and minus 3 dB.
However, I said by look into the display. Can
Yeah, I'm looking at it, but maybe I'm not thinking the same way you're thinking.
I tell you, this is the case. Right?
Right, the bottom they got unity gain, so obviously it's not unity gain.
No, that's the bottom here. You're talking the bottom here?
The bottom right says unity gain, but that's not what you're talking about.
Unity gain. What do you mean? Unity gain here?
Yeah, that's unity
Nothing
gain.
to do with that.
That's what I'm saying. So it's something else that I can't think of. So you're just gonna have to tell us.
That's what I'm telling you. Okay, now, if we're looking at point A here, what is the gain at that point? You understand it? That will be stand for the gain. That's what they say AV right here.
Oh, so you mean like 100 decibels?
Right, 100 dB.
100 dB. Oh, okay. Let me turn this to the side. Voltage gain in dB. So then that's 20, 40, 60, 80. Yeah, so that dot is on the line that's 400 dB.
Right. Now, what frequency?
The
At the-
frequency is 10 to the 0, and 10 to anything to the 0 power is 1.
that will be 1 hertz.
1 hertz.
Okay, that's what I said when you're looking into the display, you're able to identify. Okay, what is the gain? What is the frequency? Now, when they going down minus 3 dB, that means critical frequency at this point.
The critical frequency
right
at
here.
that point, yeah, the critical frequency at that point would
Right.
be 0.707 times the voltage.
Right. Okay, at this point, okay, they going down minus 3 dB, and the frequency will be 10 hertz.
10 hertz, yeah.
Okay, normally you understand in the electronic, okay, when they will be working, okay, that means the frequency have to be higher. The frequency cannot be 10 hertz, okay. So after the minus 3 dB, and now you can see the gain keep going down. If I pick one point here, what is the gain?
Did you pick where 1,000 is at? 10 to the 3.
I pick this point.
Right. That yellow dot. That's that the frequency there is 10 to the 3. So that's 1,000 hertz.
Correct. What is the gain?
The gain is 60 dB.
Okay. Now, if you keep increase the frequency, that will be a 10 times. Okay. That 10,000, right?
Right.
100,000. Okay. And 1 mega.
Right.
At this point here, okay, you can see you get a very high frequency, but the gain keep going down.
So you have zero or unity gain.
Right. Okay. So they drawing here, they telling you the slope will be 20 dB per decade. What that mean? That means they going down 20 dB per decade. Okay, 10 times. Okay. So operational amplifier, open loop gain. Okay. This is just an open loop gain. We cannot working with open loop gain anymore. Okay.
Hey, Mr. Pham, the slope where the slope goes down
20 dB.
minus 20 dB per decade, is every one of those boxes count for like 20. Is that right?
Right.
Okay.
Okay. So next meeting next week, we start with inverting operational amplifier. Okay.
All right, Mr. Pham, thank you.
Yeah. You get any question, anything? This is more easier than transistor, either bipolar transistor or JFET. Okay. The major after this operation amplifier, they will be JFET. Okay. That's almost done for the electronic. Okay, take one. Any question? Anything? Okay. If it's not, okay, so I would like to get on have a good weekend. Okay. Good night.
Thank you, Mr. Pham. Good night.
Good night.
Good
Good
night.
night. Thank you.
Bye bye.